appunto ho buttato le due cose.
Welcome back. Thank you, Giuseppe, for accepting my invitation, our invitation. And the next talk will be given by Giuseppe Longo from CNRS and also from the Tufts University of Boston. And the title of his paper is Theoretical Challenges in Biology from Cancer to Organisms. So thank you, Giuseppe.
I will try to embed some ongoing work in biology in the general reflection on which I insist upon long about the role of negative results in theory building. And by this I will start with references to physics and logic and then go to biology, mostly in a critical fashion. So I will see how the absence of negative results is really making theoretizing very difficult or large and suitable. So let's start with some references to some classical crises, I would say, the role of negative results in physics. As you know, the major successes of the equational approach since Newton brought many to believe that the mechanical systems, as they said, I mean, the dynamical system could be fully understood by the equational writing, in particular done by adding behavior to behavior by mathematical description in a linear fashion. Lagrange, Laplace, and Fourier strongly believed that by linear approximations you could solve equations, describe mechanics in all its aspects. Of course, this was a triumph of a very original, very powerful approach, differential equations. And indeed, for Laplace, the equational determination implies predictability. It's a form of completeness of the equational approach with respect to the physical world. But he knows that there are random events, little events, so Laplace, who was an immense personality, also set a mathematical basis for pure probability. The analysis of perturbation should have allowed to solve equations under all circumstances, anytime the mathematical description was possible. But this doesn't work in that way. By negative result, as Poincaré himself called it in that way, he showed that the most simplest planetary system you can imagine, one sun and two planets, yields a system where there is no integral solution, there is not even linear approximation, almost nowhere in a mathematical sense. I would like to call this a form of incompleteness of the equational approach to the description of such a simple system. But this negative result of Poincaré started a new science, that the geometry of dynamical system, which based on radically new notions such as bifurcation, homoclines, and so on. It took about 70 years to become the core of the classical approach to dynamical systems, because it was very difficult to understand what could have a randomness, unpredictability within a fully deterministic system, which was the real novelty. About the same time, there is another major crisis. By negating one of the forms, the two forms of negation of the fifth axiom of Euclid, started the new geometry, in particular Riemann is the major personality, by an understanding of what gravitation could be. It drew a new conceptual universe. As you know, at the end of, everybody knows it, the famous sentence at the end of the introduction of his habilitation, he observes that because of his theorem correlating the matrix to the curvature of space, one should think that the matrix is due to the cohesive forces, gravitation, among bodies, a real divination, as Hermann Weyl would say, because opening the way to relativity. Of course, a lot more needed to be done, in particular in time, and all what Einstein did, but really this was the basis by a negation of axioms that really was a radical novelty. Chase also proceeded, but Riemann really makes the masterpiece. To the point that Clifford, translating Riemann's thesis, insists that in physics nothing else takes place but continuous variations of space curvature. Of course, it was a major crisis in mathematics because for 2,000 years and more, the foundation of mathematics was Euclid geometry by its perfect correspondence to Lived space, but even not an issue. By this dramatic change, this major crisis, and the invention of a new area of mathematics, differential geometry, of course, the foundation of mathematics has to settle novel graphs, and then the very audacious proposal let's focus on arithmetic. Forget the relation to space and time. Forget the relation to nature. Ground mathematics on pure logic, which is indeed arithmetic, because that's fully universal, is an absolute in Frege's thinking. Even thinks that the arithmetic of Peano and Dedekind is categorical, so to say, there's only one model. It coincides with the very nature of numbers. This is blatantly false, as easily shown by Lovenheim scholar, but this was really the core of a new foundational approach. Hilbert also focused on arithmetic, but with a very different perspective. He was a major mathematician, very interested in geometry. His major book in Foundations is The Foundation of Geometry, where he fully axiomatizes all known geometries of the time and makes an analytic interpretation of those formal systems to arithmetic. That's why, the following year in Paris, he will insist we have to prove the consistency of arithmetic by finitary methods, so that also the consistency of the geometry will be proved. Very differently from Frege, he was very much interested in geometry, but he thought that a purely formal axiomatization could guarantee by proof of consistency the mathematical work founded in purely mechanical way, potential mechanizability, these were the words he was using. Again, with the idea that the axiomatic approach in the various fundamental theories, beginning with arithmetic of force and all their extension, had to be complete. One could decide any statement, prove it true or false by a mechanical proof from finitary axiomatics. Completeness again, that's the word used, which again reminds of Laplace. You have here the equation, here a statement about the future of the system, you should be able to decide it, okay? Poincaré had already shown that this was false for physics, and then Hilbert tried to recover it within mathematics. He's perfectly aware of Poincaré results, he's very happy about it, and then he tries to save completeness at the purely axiomatic level. But both approaches, with Frege and Hilbert, were on purpose made to totally disrupt any link between the foundation of mathematics and the foundation of the knowledge of nature, in reference to physics. They knew that, they said it very explicitly. And this opened two branches, one after Gödel's theorem, fundamental negative result. Gödel's theorem, that's when mathematical logic begins. You know, before 31 there are no theorems. Lovenheim scholar, compactness, very trivial mathematics. After Gödel and Turing and Church, what begins is really computability theory as an abstract theory of term rewriting. It's a matter of writing signs and rewriting them. Totally decorrelated for any natural phenomenon and any understanding of nature. We are in the frame of finite sequences of signs. And then proof theory, and then those machines that are term rewriting systems. You have finite strings that are modified into other finite strings by formal rules with no reference to the physical structure. Indeed, the hardware is separated from the software. That's a fantastic idea of Turing. You have to develop a theory of software which will become a theory of programming, totally independent from the hardware. And that's the strength, the invention of computer science, again by negative results, because they proved that Hilbert was wrong. There are improvable statements, and that the consistency cannot be proved for any theory that includes arithmetic, cannot be proved by finitistic methods. On the other hand, there is another branch of foundation of physics and of mathematics, namely the geometric frame, beginning with Riemann. This idea of genealogy of concept is found in the relation between physics and mathematics on isotropies, indeed symmetries. This was further taken up by Hermann Weyl. There is a geometrization of physics which provides also a physicalization of geometry that goes on, reaches today non-commutative geometry for quantum physics. And all these approaches are grounded on a fundamental correlation between mathematics and nature. This is measurable. If you consider Euclid, if Euclid proofs and constructions are based on ruler and compass, they are tools for constructions and they are tools for measurement. The rigid body by Riemann is a tool for measurement. So the foundation of geometry is in this fundamental interface between us and nature, measurement. which is the only form we have of access. And non-commutative geometry is based on the non-commutative property of quantum measurement. That's really at the core of this view of foundation that's what's being developed, totally disregarded by the logical formalist approach in the two different branches, Frege and Hilbert, both of them explicitly constructed in order to maintain the foundation mathematics totally independent from knowledge of nature. Then, of course, one could work freely with it, as Hilbert was very aware that you needed a mathematical tool, but he wanted to have it grounded on totally different grounds from those that allow us knowledge of nature. Fortunately, there's been a new novel encounter. That's where I worked for many years. That's semantics by topos theory, category theory, giving meaning to those formalists in a way that could be linked to geometry. But that's not what we'll talk about now. So you see, there's been something which is deeply wrong from the point of view of method. The idea that with one insight, one approach, you can say everything. These assumptions of completeness that are, by principle, for me, wrong in approaching any form of knowledge, as soon as it is sufficiently expressive, of course, like equations or like axiomatic systems which include arithmetic. There is a deep parallel between Laplace completeness and hypercompleteness. Then there were the no's that were opening new ways. It doesn't mean disregarding the previous approach. They have a relevance, but they are limited. Then it's really been a surprise for me, after a lot of work in mathematical logic, in a Gödelian frame, searching for meaning in geometric structures, and after collaboration with physicists, bump into biology and see that for the third time there is a completeness assumption that dominates the field. The DNA is the complete set of instructions for ontogenesis. We will see that in more details. That's the central dogma, that's the stereospecificity, that's the one gene, one enzyme assumption. Once more, you know, the first time was quite fantastic and justified. You know, equational approach, Newton, they were predicting Halley comets, discovering Neptune. I mean, that's fantastic. Differential equation are still now the Rolls Royce of mathematical physics, no doubt, even though they are complete. The axiomatic approach, I would say, is less interesting, but still, you know, it made major clarification. It taught us to give good definitions. It was very important. In the 19th century, Cauchy, Poinsot got wrong theorems or wrong proofs or right theorems because they were not able to give good definitions of continuity or uniform continuity, for example. So the axiomatic approach taught us to give good definition, which was also a concern for Hermann Poincaré, for example. And so, but the third time, they are getting to be a little ridiculous. I mean, you know, you can't really iterate with the same. And it's always a matter of writing, because it's the writing of equation that's assumed to be complete. It's the writing, finite writing of axioms that's supposed to be complete. And it is the writing of the genetic structure. That's the surprise is that specificity, genetic specificity, is written not with ideograms like in Chinese, but in an alphabet. This is shortcut. It's quite amazing. With major consequence. I mean, I will try to hint catastrophic. That's been, I think, is now, still now. Because when money encountered this frame, you really get into a diversion of sides. Now let's go to about the incompleteness of the molecular descriptions from Schrödinger to central Rocco. Many attribute to Gödel, to Schrödinger, this idea of the coding of the phenotypes in the DNA. It is right, but Schrödinger starts with a major concern. He sees that geneticians, there was already a lot of work since the beginning of the century on chromosomes. Geneticians were capable of seeing and inducing changes, mutations in the chromosomes, and they derived it from these positive connections. In particular, there was a result that I will quote by Wedel et Tatum, very important one, in 1940. They had observed that then they were able to induce a mutation and observe a change in a protein, actually in some enzymes, and they had deduced from that one gene, one enzyme. Schrödinger doesn't like that. He knows that by differential experiments, you cannot derive the rule. And then he says, we have to make a positive proposal, and he invents the idea that the chromosome could be a code script, you know, encoded information. And he knows what he's saying. In calling the structure of the chromosomes a code script, we mean that the open-penetrating mind, once conceived by Laplace, could tell from their structure how the egg will develop, etc., etc. So again, you understand what he's saying. If I'm right, and there is a coding of the phenotypes of the organism we will be in position of the Laplace conjecture, the completeness of the description. That's why in the second part of the book, which is not much quoted, which is beautiful, he takes a totally different perspective. He begins by saying, forget all what they said about chromosomes, and develops a very fine analysis about negentropy that work done with a colleague of mine a few years ago, and which is another. He's just trying, he's proposing, and he knows what he's talking about. Indeed, the Laplacian structure of term rewriting systems, because these are computable systems, term rewriting system, was very clear to Turing as well. He explicitly says in his 1950 paper that this machine is Laplacian. It is deterministic and predictable. You may implement the most crazy turbulence on your screen, the most unpredictable deterministic phenomena you have in nature. You push for a start, it will do exactly along the same trajectory. This is something which is not enough said. This is due to the discrete structure of the machine. Again, I insist, because many colleagues that do simulations don't know that. If you have a turbulence there, the most chaotic process, you push for a start, it will go exactly along the same trajectory. Because what is missing in the discrete data type is the issue of measurement. Unpredictability pops out in classical systems because the interface of nonlinearity and measurement is the approximated measurement, the interval below which a perturbation fluctuation is not seen. It's that perturbation fluctuation which is amplified by nonlinearity, which gives the predictable event. Poincaré said that in 1902, say, and then we have random event. Randomness in classical dynamics is due to the interface between nonlinearity and phenomena by measurement. When you have discrete data types, this second point disappears. The most wild nonlinear system you have here still gives perfect predictability, at least by iteration, identical iteration. Of course, the situation is different in networks. In networks of computers, because you have space-time that we understand better by continua, then there is a lot of randomness. But because the nodes are discrete state machines, we can avoid it. And they work. You iterate. You look at the web page in California 10 times, and it's always identical. And it follows always different paths. There's a lot of randomness. But my colleagues are very good in concurrency by semaphores in the living, totally avoid randomness. They call it noise, and it doesn't exist anymore. Of course, this has nothing to do with nature. This has nothing to do with biology in particular, where I will insist that if I have time, randomness is at the core of variability, which is at the core of diversity, which is at the core of biological stability. So, in a sense, organisms are the exact opposite of these machines by the principles that are the machines. Typically, another fact is that by the software-hardware split, we can transfer the software of a dying machine to another machine, compilers, operating systems, everything, and this is a sort of metempsychosis. I think it's totally compatible with biology. You see, however, unfortunately, this paradigm was brought into biology. So the two major theoreticians, first Monod Jacob, there are a few more. I refer to them a lot because they are very deep. They theoretized. Most molecular biologists simply don't theoretize, and they have the implicit naive theory, which is wrong by principle. But some of them did theoretize, so I refer to them. I refer to them because they're good. They say something. These paradigms are still valid for 90% of molecular biologists. Not the other biologists. There are alternative ways, fortunately. Molecular processes are Cartesian, even not Laplacian, Cartesian, autonomous, exact, independent from internal influences. He gets to say that gene expression is independent from metabolism. You know, even our ancestors 10,000 years ago at the intuition that bees and ants modify gene expression by metabolism. This because there is oriented transmission of information. How do you transmit and elaborate information? By exact state-specific interactions, chemio-physical interaction between macromolecules that act like a Boolean algebra, like in a computer. Genes define completely, here's the completeness, the three-dimensional folding of proteins. The epigenetic environment only excludes the other possible foldings. Evolution originates by noise, imperfection. And of course, when something is predictable and deterministic, it's programmable. The concept of program, the concept of program, gives me now a legal status to the Another biologist of neo-Darwinian approach theoretized information explicitly by referring to the two major frames, Turing-Kolmogorov, elaboration of information, and Shannon, transmission of information. I worked quite a lot in the first one, and this paper at least makes a reference to two scientific frames for elaboration and transmission of digital information, because that's a core point. We are all talking about discrete state machines and digital information. That's the focus on molecules. Unfortunately, it gets it all wrong, typically because these two theories, for good internal reasons, treat the relation between complexity and entropy in a different way. In the case of Kolmogorov-Shannon, complexity and information is covariant with entropy. In that case, it's contravariant with entropy, while Smith doesn't understand this. He gives an example for one that he refers to the other. That's the status. I wrote these remarks in the paper. I may give you the reference for this. That's the status of the role of information, which is derived both in the transmission and in elaboration into very robust, beautiful theory of digital elaboration and information, but that used from common sense uses, not on the scientific uses. The only time they are explicitly mentioned deeply, they are mentioned in a wrong way, and they are not used consistently. Which is the core point. I got really surprised when I learned about the central dogma. Is that there is this one-way transmission of information, elaboration, DNA, RNA to proteins with some vector arc. Because how could one think 8 years, 7 years after Poincaré that in a quasi-turbulent situation like the proteome of a eukaryotic cell with a quasi-chaotic enthalpic oscillation of macromolecules, something goes through linear between interaction. The main part of all of this that made us forget genetics, because you see, a lot of people, Paddington, Barbara McClintock in Italy, my friend Marcello Gugliatti, did all their life work on chromosomes. Chromosomes are very important. They are the chemical physical trace of a history, of the history of evolution. They're used permanently by the cell, but they always look at them in a context, the context of the cell, of the organism, of the ecosystem. These were totally disregarded and forgotten for 20, 30 years. Even for regulation that was first discovered by Barbara McClintock, known Jacob and Cotter, because they look at regulation of DNA inside DNA, and they succeed in finding one case. The operon lactose experience is fantastic, incredible insight, extraordinary protocols. It's a case where the genes are regulated by the genes. But then what if one asks, who regulates? Which is the regulation of the gene regulating the genes? Oh, there are other genes regulating the genes. So this is the core principle that goes to the phenotypes, because as proteins are always structures, phenotypes, you go from DNA to one way, to phenotypes. As I said before, this was where Schrödinger was posing the problem. How can we get to this by the differential method? As I said before, Beddoes and Tatum had those very, very audacious analyses for which they were deriving from a mutation, a change in the protein that were affecting the phenotype. But how to dare to derive positive connection, one gene, one enzyme, as we know that most proteins in a suitable context may become enzymes, and we happen to have 1 million proteins and on 20, 25,000, 30,000 genes. The number is not fixed because the notion of gene is not well defined. Every Fox-Geller shows how in a century we changed it 5 times, the definition of gene. Even Pauling, a Nobel Award, in 87 still believes one gene, one enzyme theory, which is at the core of this unidirectional transmission. So all this conceptual frame about the completeness of DNA was really carried on for decades. And this frame that you go one way, the causal structure, as a term rewriting system, as a Boolean algebra, as a computer, as I mentioned before in the quotations, allows an idea of reverting. Anytime you have a phenotype, you have to look at the corresponding genotype. This is the completeness assumption, the search for the gene of. So not only any phenotype has an antecedent in the genotype, but the genotype is complete. We have seen the word. It is a complete determination of the phenotype. Indeed, during the work for decoding the human gene DNA, one of the protagonists, W. Gilbert, stresses, once decoded the DNA, we will be able to transfer in CD-ROM, decoding and say, here is human being, this is me. Quote. And of course, till now, the entire approach based on the new synthesis insists that selection, targeting on genetic information, organisms are vehicles, they are avatars. And then the philosophy of the selfish gene, but this is even not worth mentioning. The completeness is there, it comes back over and over. A few examples of the gene of that I looked closely at the first one. The gene of marital fidelity on Nature. A colleague of mine made a close analysis of what this happens there. In some mice, you have, in some population of mice, you have real fidelity. They couple once and then they stay forever together. But they had discovered a mutation and those mice were no longer faithful. It was a real masterpiece for what happened in the population. And it was considered in paper a gene of marital fidelity. Journals then transferred this to humans, of course. My colleague made a close analysis. The point is that this mutation was disrupting the hormonal control of olfaction. And now those animals recognize each other and do almost everything by olfaction. Okay, call this gene of marital fidelity. The longevity has been 15 years. Only recently the authors acknowledged that the experiments were biased, that indeed there is no way that in general by silencing the gene we could live 50% more, is what was conjecture. Obesity is a very funny story. I know it because I was in New York and a friend of mine was working there. She was also on Italian TV, as she still is, very pretty woman. They showed her one mice and another fat one, the gene of obesity. She told me, we send correspondence, but we could sell the idea to the pharmaceutical industry for a lot of money. So, we know that this is correlated about 8–10% of cases of obesity. All the rest of obesity goes from psychological problems to societal problems as well. These are cases I know closely. A former molecular biologist made a collection of gene of which I don't know anything, so I can't say anything. The most interesting is about academic freedom. You should look at the book, it's real fun, because it did work in that itself. So what's the problem? It is myth of complete digital information. The point is that they believe that the stability and organization of DNA and subsequent molecular cascades completely determines the stability and organization of the cell and the organ by its complete informational content. Is totally false. Because the very stability and the organization of the cell and the organism causally contribute to the stability and organization of DNA first, the DNA itself, and the subsequent molecular cascades. Again, incomplete, doesn't mean useless. Well, it's like after Poincaré result, we didn't say that differential equations are useless, but surely not. And also the axiomatic approach is not useless, less important than differential equations, but it did teach something to us. And DNA is extremely important. Is, as I said before, physical-chemical trace, a template for proteins production in a cell that uses it during the entire life. It's a constraint. in the most fundamental internal constraint. There's also the membranes and all the structure that is there, but this is an extraordinary constraint. But it's incomplete, it's surely not instructive as a constraint used by the cell. I will now refer to some work on cancer. It will be troubling for some of us for sure, because that's a terrible disease whose incidence is increasing. Even though in the last 25 years, doctors that are very good have been doubling the success of therapies, totally independent of any biological foundation, just by clinical experience and by technical devices. They can go in the body with the camera and they inspect the tissue, they use laser operations. So external technologies, lot of experiments, clinical experience about chemotherapy, no connection to genes, they affect reproduction by affecting polymerization of microtubules, so completely different, without real theoretical knowledge, but with a lot of fantastic clinical experience. The progress are enormous, and yet the rate of death by cancer is stable, in spite of the doubling of this theoretical success, which means the increase of incidence. So this is a big issue, and I think that it is absolutely evident that we have been made blind by this wrong perspective on biology, the computational, formal, analytic perspective. I will mostly quote now, not to seem too much imbalanced, I mostly quote the fantastic autocritique of a major personality in cancer research, Robert Weinberg, who is at MIT, that in a famous paper of 2014 made an amazing autocritique that I will spell out. But let me present the personality. He has been a leading personality, a leading scientist, a leading biologist in so-called somatic mutation theory. The idea that totally gene-centered analysis, in order to understand cancer, we have to understand the mutation that made a cell, one cell, crazy within a body. And so he wrote a paper in 2000 where the genome was almost decoded, was already decoded, as a matter of fact, a real triumph. 7,000 citations in few months, where he says, we got it. Now that the DNA will be decoded, we will understand everything, in particular by looking at the DNA of cancer cells. We will make a diagnosis, a prognosis, therapy, everything. In 10 years. 10 years is not he says, it's Collins, I will quote Collins, will promise that. Anyway, cancer biology will become a science with a conceptual structure and logical coherence that rivals that of chemistry or physics. 7,000 quotations, because he was a major personality in that approach. Then he writes a paper coming full circle from endless complexity to simplicity back again, which is the story of recapitulation. We were all reductionists. We would parse cancer cells down to the smallest molecular detail. Half a century of cancer research had generated an enormous body of observation about the behavior of the disease, but there was essential no insight into how this disease begins and progresses to its life-threatening conclusions. Essential incoherent phenomena that constituted cancer research at the molecular level bring us to say that one should never, ever confuse cancer research with science. You remember, he was saying, now, with the decoding, and 14 years later, this is the exact opposite. How the story begins? Well, in 1970, these people, including Weinberg, was a very young researcher, convinced Nixon to start a war on cancer. The promise that was that in 1976, the bicentennial of the American independence, they would have had genetic therapies for many, if not all, forms of cancer. The idea was that retroviruses were inducing mutations and causing cancer. Well, few were seeing the terror, but the well-established observation that most types of human cancer did not represent communicable disease. Cancer is not infectious. Yet proposed retroviruses. They happen to be infectious cancers. Papillomavirus, well-known cancer of the uterus, is caused by a virus which is not a retrovirus. A few retroviruses have been recently discovered to be cancerogenic in Polynesia, specific carpets. It's very rare. They gave the responsibility to that. And then they claim, oh, well, no, it's not retrovirus, but some chemical species induce mutation. They are mutagenic activity. So the reference to the ecosystem finally. But then we discovered by the end of the 70s, indeed a little later, this was confirmed even more, that most human carcinogens are actually not mutagenic. And then he adds a fantastic sentence. But fortunately, I and others were not derailed by these discrepant facts. Yet they insisted it is one mutation in one cell that begins the process. Well, then they went to many mutations. And then we go to 2001. You see the story, always the focus on DNA, continuous changes of perspective, observing that it derives from an infection is quite amazing. You know, Ramazzini, the fantastic anatomopathologist of the early 18th century in Italy, in Bologna, who made an almost complete list of cancer. Because, you know, the cancer that kills you, except leukemia, except some lymphoma, is visible at autopsy. He knew that, and he knew that it was not infectious in early 18th century. They had forgotten. And this was the first step, as I said before. Then goes to mutation, and then the idea is that chemicals may induce mutations that are mutagenic. Then gets to 2001. Indeed, the triumph, Collins, the head of the public project, you know there were two projects, one head by Collins and the other by Venter, which was a private enterprise, and Venter won the competition. But anyway, Collins was already advanced a lot. So together they announced the full decoding in presence of Bill Clinton, Blair on Skype, and Collins insisted in 10 years we will have therapies for all monogenetic diseases and for cancer. As I told you, the idea that was developed during that time, we fully encode the human genome on a CD-ROM. That's the idea of personalized medicine. You go to the hospital, they encode your DNA, you can go home, the compact disc will be going around in the various departments, and they will propose therapies and so on. The perspective is that instead of having doctors examine the disc, you have computers. So you have medicine with no patients nor doctors, which of course would be very convenient. Still now, there is a project they launched recently about personalized medicine in these terms. As I said, Venter had won. He was much more careful in announcing the success, which is a major technology success, knowing the exact chemical structure of this incredible, fantastic trace of an entire evolution is a major success. I would never deny that. More a technology than a science, but still a success. Then Venter wrote a paper for the Spiegel. The title is, "We have learned nothing from the genome." And this paper is not known. I mean, it's amazing. He quotes Funnies, his colleagues that in 2000 had announced the understanding of everything, in particular of cancer. He uses the word. Go please, write to me, I can give you the link to the interview by Venter. You know what he's doing. He's a smart man. He knows that you can do something with bacteria. There is no software hardware. You have to transfer hardware. So it is only matter. In biology, there is only matter. So he's combining fragments of DNA of different bacteria, putting them in bacteria with no DNA in order to obtain specific targets. He's aiming now at bacteria that can eat oil for spills, you know, in the sea, for example. I don't know if it works, but if it works, these things are very important. They could already produce insulin, which is very important in this way. That's where you can really intervene on specific target and on bacteria. Because there's not much more than DNA, proteins, and there's no complex structure of the bacteria itself. Indeed, we did learn a lot from the coding. We learned that in the same tissue of cancer, the mutations are very different. It's a total mess. They are polyploidy, lots of chromosomes, aneuploidy, wrong number of chromosomes. That's always present in most 69% of cells in a cancer tissue. These phenomena are heavily present. But when you look at two cells that are closed in the same tissue with cancer, there's no way to find the uniformity that would allow, as what it was promised, a diagnosis, a prognosis. No way. And of course, this diversity of mutations is a major challenge for therapy, because those cells react very differently. However, what we know since clonation of mice, which is a success of cellular biology, not molecular biology, is that if you look, if you take few cells from a sick mouse and you put it in a same tissue in a cloned mouse so that it's not rejected, they get to normalcy. So a cell which has been heavily affected, being in a cancer tissue, when transferred in a healthy frame, works normally. It doesn't need to go back as for the DNA structure. It uses what's needed by DNA. And the conjecture of my colleagues is that the surrounding cell, by the permanent molecular changes that happen in a tissue, provide the right proteins to the cell to work correctly. But this we don't know yet. Look at another case where, which motivated Weinberg autocritique. When Maltoni in Italy looked at asbestos, and he observed that it was cutting the intercellular connections, cutting cell membranes, and he said, well, this is cancerogenic. The answer given by the theory was, no, you have to show us the signal that goes to the DNA and deprograms it. Otherwise, you don't prove that it is carcinogenic. Now it happens, and that's the motivation for Weinberg observation, which applies to lots of carcinogens. If you reduce asbestos in powder, so you destroy its physical structure, but you preserve the chemical one, it is not carcinogenic. Of course, it's not good to breathe the powder of asbestos, but it's not carcinogenic. And it is so. Lots of experiments now on lots of carcinogens. The chemical structure, most of the time, not always, polychemical structure is not a carcinogen. The key point with cancer, that 90% of clinical cancers are carcinomas or adenocarcinomas. The cancer arising in epithelial tissues. And the insight of my colleagues are giving is to look at the stroma, which regulates the epithelium is made of two basic structures, a proper epithelium and the stroma which supports it, which regulates reproduction. And now, as I said before, there is a massive evidence of reversing to normal of individual cells, a group of cells, which shows that when you place it on a healthy epithelium on a healthy stroma indeed, because now it can transfer also fragments of epithelium, and the epithelium takes the shape of the new stroma. Is the stroma that regulates the structure. This gives, together with lots of evidence, the fact that metastases are not due to the migration of one cell, but you must transfer a full fragment of a cancer tissue, which happens all the time. We always have in the body pieces of tissues that move around everywhere. For example, there's a lot also moving from the mother to the child and vice versa. Lots of mixture of cases of this type. Fragment of tissues are the origin of metastasis, which is very important because more than 80% of death by cancer are due to metastasis. Very rarely primary cancer are lethal. So let's now go to the theory building after this critique. They encounter, this happened, that encounter between me and my colleagues some 7, 8 years ago, who were in Paris because they discovered the carcinogenic effect of bisphenol A that you may have read on the newspapers because it was present in all plastic for food, and discovered that 20 years ago, 10 years of a major battle in the States. Because you know, when you say that a material that is chemical that is produced by 2,000 tons per year, and you say it's cancerogenic, you have a lot of enemies. So they said that it was naturally produced by cells, by yeast, for example, and other people showed that it was actually produced by the container where the cultured yeast was developed. So they had this in the background, and fortunately now also in Europe it's forbidden because of the audition they had after the American Senate, also the European Parliament, and the French Parliament. France went very much in advance about these things and other endocrine perturbators. But discussing, I mentioned to them an analysis of complexity in evolution I had been doing with a colleague of mine, Francis Bailly, which gave us some criteria for measuring anatomic complexity, phenotypic complexity. You know, the dead animal, you can measure the complexity. You can count, it's very epistemic, the number of tissues. You can count the fractal numbers, lungs, vascular systems. You can count the complexity of networks. You can attribute a number to an animal or to a plant, we didn't do that, animal, by a reasonable, very epistemic choice of a complexity measure. This was done to understand Wood's claim that there is a random increase of complexity along evolution. I will not get into details, but he could prove that this is due to an asymmetric diffusion equation of a variability density function which distributes randomly, but in an asymmetric way. So for this asymmetry, we have an increasing complexity by totally random reasons, which, however, goes on. You cannot say how an organism will complexify, but you can say that on the average, organisms will complexify. So he made an analysis, mathematical analysis of complexity. We set on mathematical ground a very beautiful work done empirically by Gould. Typically look at the bronchial system, lungs, you can compute the fractal numbers which optimizes exchange of energy and matter in a volume, so a fractal number of 3.2 for vascular system, bronchial system, or 2.6 for the lungs, that optimizes the exchange of energy and matter through a surface in a volume. But if you compare to the lung of a frog, which is fractal dimension 2, you can say 2.6 and 3.4 are bigger, so it's more complex. Then it happened that together we observed that this is what happens in cancer. You see, the lower image is a cross-section of ducts of a healthy tissue. Above there is a cancer going on, and what happens is there is an increasing of lumina. So topological numbers increase. There is an increasing complexity of the tissue. This is the case of tissue. You can say the same about epithelial structures. So in the presence of a tumor, what happens is that those numbers we had, all or part of them, according to the phenomenon of certain cancer, increase. And in our analysis, we still have really to check it. In our analysis, cancer is the only disease where an increasing phenotypic complexity, atomic complexity, goes together with decreasing functionality. In all other cases, they both decrease. The functionality of a tissue and organ decreases together with complexity, but cancer seems to be the opposite. This concerns epithelial tumors, but they are the vast majority. This gives a kind of hallmark which leads to our reflection on cancer. They started well before me, they set the basis. With me, we made a connection to evolution, to the theory of evolution. It is an evolutionary process. In a sense, it's normal, quote unquote. It is as if, to put it very shortly, but it's wrong because it's too short, it's as if a population of cell was escaping the control of reproduction, which is very strong in an organism in contrast to an ecosystem. So an ecosystem also controls the reproduction by the interactions. But in an organism, this is very, very firm, differential control of reproduction. Brain and heart, almost no cellular reproduction, intestine a lot, the liver, so hormone system, tissue matrix, cell-to-cell dialogues, immune system, control reproduction. Something interferes in these three corners correlation, tissue, organism, ecosystem, carcinogenic interference, control of reproduction, cells react, as always cells under stress, reproduce with variation as much as possible. Well, I don't get into details in the theory which gives a particular relevance there. Theory, Toft, tissue organization field theory, reference to the interference of control of epithelial cells reproduction by the stroma, which is more and more accepted, in particular, fortunately, of the many groups that now work in this frame. There is a very strong one at Bethesda Hospital, which is the major center for cancer research in the world. It's a group working in their approach. Of course, there may be mutations originating cancer, but that's very rare. Most of the time, mutations are a consequence, but these evolutionary reactions of cells that, under stress, reproduce as much as they can, when they can, with variation, and variation means mutations. The point is that, as I mentioned already before, now that we can decode the DNA, it is evident that cancer is not clonal. It comes from many cells in the same tissue, that the mutations are all different, that the growth is evolutionary system, correlated to evolutionary growth, in particular within an organism. It may reach, at least the top speed, may reach the speed of embryogenesis, which is a lot, as you understand. However, this work really goes to a frame that already existed, but was totally disregarded. I mean that those people didn't get jobs, didn't get funds. Cancer is no more a disease of cells than a traffic jam in a disease of cars. A lifetime study of internal combustion agent would not help anyone to understand our traffic problem. Again, it's not the cell DNA problem, it's a tissue problem. That, of course, it is a problem. Because if you are in a traffic jam for too long, also you range in many problems. We have learned very little about causes of cancer from the study of proto-oncogenes and tumor suppressor genes. These were the two notions that has been leading and still now leading. 2 weeks ago, particularly in the Italian newspapers, in our stampa was a full page, quoting a paper from Cambridge researchers published in Nature, mentioning the 23 genes that cause breast cancer. Of course, the paper was referring to mutations and to the fact that there was an expression that could be correlated to the ecosystem. Again, gene-centered, fairly incomplete analysis, wrong causal directions. However, it was cautious. In the newspaper, not only in Italy, but everywhere in Europe, it appeared as the genetic causes which was confused with hereditary. Because very often, journalists in particular, when they say genetic, they mean hereditary, and people believe that. So the idea was that, you know, you have got them, there's nothing to do, and then you have breast cancer. Why was that a few weeks ago? Because there is an ongoing discussion in the European Parliament discussing about endocrine perturbators that are a major cause by disrupting the endocrine system, which is a fundamental controller of cell reproduction, of all sorts of cancer, in particular breast cancer. It is the domain of research of Carlo and Anna. The point again is this approach, the gene-centered approach, very easily, not necessarily, goes to the idea that is hereditary or that there is nothing you can do except perhaps invent reprogramming DNA, and that the environment has little to do in a situation where instead we are really having major problems with the environment. Why? One of the reasons is that we didn't see the disrupting role of the 80,000 molecules we produced in the 20th century. 82,000 for to be exact. The Congress in the States asked for a report, I can give you a link to it, in 2008, and there was a full study to which my colleagues in Boston participated, made by hundreds of people, and they reported 82,000 molecules that been putting into the ecosystem. But you know, molecular biology was saying, there's no problem, many of them are small molecules, they are not stereospecific. Specificity of biology declared was that Cree, or I don't think it was one or Jacob, is entirely in the stereospecificity of molecular interaction. So no problem, this molecule will not interfere. The situation is very different. Macromolecular interactions are largely stochastic. They are given in probabilities, and the probability depends on the context. You modify the context, you modify the hormone cascades, you modify the interactions between macromolecules, hormone molecules, and cellular receptors. One of the consequences you may have read on the newspapers, an amazing one, is evolutionary consequence. That's, for me, important at the evolutionary level. In 60 years, the spermatozoa density in Western men decreased by 50%. It's incredible data. It was in newspapers and it was regarded. What is said by a very strong declaration of the Endocrine Society in the States is that it is caused by finite combination of these 80,000 molecules. Now, how to find them? It's not easy. I want to skip the part on bisphenol A, which was in a sense a success because now it's been forbidden everywhere. Let me briefly conclude on cancer, then make just one more remark. Of course, it's very easy when you use this common language of information, programming, reprogramming to explain to politicians. Even Nixon, even Bush would understand when you say, you know, we are going to reprogram the cell. And they put a lot of money. And indeed, a colleague very honestly told me this, look, don't be so critical with these words we use, because that's the only way we get money. Now, the investment in research is decreasing everywhere. We can save at least molecular biology if we keep using these words. Politicians understand them. But again, there were people in disagreement, but small minority and nobody referring to them. Oh, by the way, the first paper by Weinberg had 7,000 quotations in a few months. Apparently, 2 years after, he has few tens of quotations, the autocritical by the same person, the same prestige. More seriously, the overall result, the semantic mutation hypothesis has been the effects of research on research workers. It acts as a tranquilizer on those who believe it, and this is a time where every worker should be loaded now and again, basic ignorance of what cancer is. It is difficult to get a man to understand something when his salary depends upon his not understanding it. That's the point. There is too much money or project already oriented in this direction. You know, it's like a huge ship going in the sea trying to divert this. Very difficult. And again, you know, Popper's idea that you falsify by data theory is totally wrong. Theory changed because of a change of metaphysics. You know, we didn't move to Kepler and Copernicus because of data. The Arabs had many, many more data during this beautiful 3rd century of Arab astronomy, Copernican style. Many more data than Tycho Brahe. They changed it because there was a change in metaphysics. And now we need a change in philosophy of biology. One final consequence, the GMOs. The GMOs are the direct children of the central dogma, the idea that the DNA you perfectly guide an organism. Yeah. Disregarding the non-complex interaction in the ecosystem. And now we know that, for example, one aspect where I learned something from my friend Marcello Pugliatti is that there are major catastrophic effects on microbial flora and fauna, fungi, roots, soil. That is increasing evidence. Again, because DNA is always in a context, its expression depends on the context, the effects depend on the context. And the context in the case of plants is rooted in the roots, among other things. And that's where probably there is the most negative effect, much more than contamination and so on. It's, this is long-term, severely affecting the soil. We have our way out. I will conclude with it, is to move from central dogma to interactive perspective, tissue, organism, ecosystem. Going back to Darwin, you see, because Darwin is quoted mostly for selection, but that's the second principle. Second principle, we choose Darwin's observables, organs and phenotypes, and that's a little bit work. The first principle of Darwin is descent with modification, 3 chapters out of the first 6, 3 chapters. And that's revolutionary because Buffon and Lamarck believed that modification was induced only by the ecosystem. No, insists Darwin. Even in similar conditions, any reproduction gives changes. That's the origin of variability, diversity, and stability, because diversity is stability in organisms and in population. And then selection of incompatible. We brought a look in comparison with physics, and Hamilton synthesis work on the conservation principle, energy, momentum. That's why I can use the variational method for the Lagrangian. At the same time, Darwin, who fortunately didn't know Hamilton, centers biology on a non-conservation principle of phenotypes. This is evolution. And the idea that we bring to an organismal perspective Darwin's view, also in an organism, the default state is reproduction with variation. The principle is that biological dynamics are never identical iteration of the morphogenetic process. And the organism controls reproduction with variation. As I said before, tissue organization, cell-to-cell dialogue, hormone system, immune system in a differential way. You have to think differently the condition of possibility for biological theorizing, and that's the perspective we are developing. Okay,
Thank you, Giuseppe. Okay, now the session is open to discussion. Question from?
Yes, Julia.
Julia.
Thank you very much. I really appreciate this way of presenting such a long history, a long path, which mixes in a very profound way also theoretical biology with philosophy. I'm not so sure that the metaphor of the code actually is the problem as a metaphor. As I would say, that is really the theory underneath, as you showed. So that's just because, for instance, when you pass to the epigenetic way of seeing, you find exactly the same problem. So why? Because in 2015 at the conference in Uppsala, organized by Cellucci and Katinka Eberts, they were actually saying that the epigenetics was bridging the gap in nature and culture, and it was quite obvious that there were two main issues. The first was that actually activating the epigenetic mechanisms at a certain tissue level wasn't possible as a model to be applied at another tissue level. So this is really aligned to what you're saying with Soto and Sunashine. The other thing is that when you look at so complex mechanisms, for instance, that they were presenting about the schizophrenia, and they were using basically animal models like rats to discover problems of schizophrenia, so at another complexity level. So that's for me a way of putting the idea that the methods actually are always embedded in a specific epistemological background, because epigenetics has been presented as something completely different and a change and a shift. While the other critiques that you can make at epigenetic paradigm is that you completely forget the importance of the environment. Because you give, from a sociological perspective, you give the moral problem to the mother who is smoking, or to the father who is having an attitude which is probably transmitted as a not defensive from stress to the son. But this is completely disentangling the perspective, the theoretical perspective, from the background of the environmental issues and the sociological issues. Okay, then I have many other things that we can discuss.
You know, epigenetic has had so many meanings, because at first we just consider the proteome, basically. Something which is a cell is not DNA, but then it enlarged very much. It's flexible notion, it goes everywhere. I can't really say. What's sure is that there is always, at least approaches I know, this reference to the digital structure, which is necessary in molecular. That's what they aim at here. In spite of the massive evidence that is functional to gene expression, the pressure, the torsion on the chromatin, which may be the pressure and torsion on the nucleus, which we understand better by mathematics of continua, typically. the context of the cell is fundamental in the use of the DNA. The observation now, massive evidence, individual cells or few cells from a cancer tissue transferred to a healthy tissue work happily, and the DNA remains a mess if it had become a mess. The cells, by the context, by the interactions, by the novel situation in pressure, in cell control of reproduction, uses the DNA in an acceptable way, roughly acceptable way. So the epigenetics doesn't need much, depends on the school, but the problem again is that they use the coding all the time, which only focuses on molecules. By these abuses, I mean, when you use words, information, programming coming from a science, they cannot be used naively, because you bring in the structure of determination of the science, the Laplacian structure of determination, which is at the core of molecular biology. There's a Laplacian structure of determination. With noise, and also Laplace was, as I said, was aware that there is noise. The analysis of probability is about that. Nothing to do with determination. Why? No. First of all, because there's a constant role of physical structures, deformation, pressures, and so on. Second, because the very word noise gives a negative connotation to randomness, while variability and diversity, as I said, are functional in biology. They are functional in a population. A diverse population is more stable. In an organism, you know, by decoding a fantastic achievement, we now know that 50% of a liver, which is a very dull organ, if you look at the liver at the butcher, it's very dull. 50% of those cells are polyploid, aneuploidy, they have a wrong number of chromosomes, all marks of cancer, by the way, according to the 2000 paper by Wenger, 50%. And this is functional, because they react with different enzymes to the continuous toxic shock we have. Diversity is functional everywhere, not to mention the immune system, where productionized diversity is the core, it's functionality, that's the other extreme. So the calling noise in a computational frame is conceptually wrong and brings all sorts of mistakes. As for the context, of course, this is what matters when you see similar cancers in a family and they refer it immediately to the genes, and then you discover that those people have been sharing the same kitchen, the same plastic, the same environment most of their life, then you should refer to something else. You know, like ILVA. Now we don't discuss it anymore, but the rate of cancer death is 65% against 32, 33. The rest of Italy, 65% is this rather ecosystemic in an area as large as Bologna. And saying Bologna because I was telling that Center Ramazzini for Cancer in Bologna, where they made an analysis of the situation. So the consequence of those approaches is reducing or even disregarding, mostly in the journalistic account, newspapers account, the environmental causes, which are very well known. Ramazzini knew a lot of them in the 18th century, and they're regularly disregarded to say with molecules produced by our industry, we will get to genetic therapy. Now, a few weeks ago, there's been a new alliance between Monsanto and Bayer. That's very scary. They will put 100 million euros or dollars per year in research all in this direction. It's very frightening, very frightening.
Other questions?
Yes. Yes, can I follow up the question about research funding? You see, what your papers seems to suggest that there's a dominant research program in cancer research, which is based on the idea that this has genetic causes, that it started by the DNA being disrupted. And the problem is that this work is not producing good results, but it's very difficult to change away from the dominant research program. Well, what I would say, I know nothing about this case at all, I hasten to add, but that seems to me a typical situation which you meet, actually, in all sorts of branches of research. You tend to get one dominant research program which gets all the funding, and minor alternative research programs tend not to get any funding at all. Now, if you want, my view would be that the root cause of that is due to the way funds are allocated. And there is very simple model. You see, funds are normally allocated by, you have competing research programs, and they're judged by peer review. But if one program already dominates, the majority of the peer reviewers will come from that program, and they'll think quite genuinely, not being dishonest, that other approaches are wrong. So what I'm saying is that if you want to get out of the situation, it's not just intellectually, you've got to think about changing the way research funds are allocated. So I wonder how you react to that point.
Yeah, well, there is a whole story about that in the sense that biology till the 1940s and 50s was a very poor discipline. You know, few people looking at butterflies, excellent evolutionists, with very little money with respect to physics, for example. Then, with the arrival of molecular biology, in the lack of a theory of our areas, because we have yet, since 150 years, a beautiful theory of evolution, but no theory of organisms. Suddenly, money arrived, because molecules can be produced by pharmaceutical industry. So molecular biology got a lot of money in absence of theory. So in physics, you may have biases due to money, like probably high energy physics, this is surely the case. But you know, the theory is very robust. You don't divert to relativity theory or quantum physics because of, well, perhaps you will one day. You need money, it's not enough to destroy this robust theory. In the lack of a theory, that money has been totally concentrating research on molecules, on what is the core molecule of organisms. As I said, even geneticians like Waddington, Barbara McClintock were forgotten because they wanted to understand the context, the cell, the organism, the ecosystem, focusing on molecules, money getting there. So I totally agree with your paradigm. In the case of biology, there's something more. The something more is again money before theory. And then the theoretical frame was totally, before philosophy if you will, it was totally distorted. And it's so important having this money. You know, in the States, cancer research, including clinical, which is different, clinical research, is 10 billion a year. Kind of amount of money. And most of it goes this way. When you have Monsanto and Bayer together, what can you do against the money they put? Look at the example I said before. This discussion ongoing in the parliament about endocrine disruptors, all the European newspapers, almost all European newspapers pop out picking up 1 out of 10,000 papers on cancer you have every week, because there are 2 million papers on cancer. Picks up 2 or 3, make a full page. It is genetic, thus, says the journalist, which is not in the paper. It is hereditary by those people who want to discuss endocrine disruptors. It's different from other areas. It's much more severe, and it's a big problem. Have you seen those autocritique and Venter, what he says? Nobody cares. Venter and Binder, those founding fathers that say, we have understood nothing, we have to change direction, or make a lot of money with bacteria. Venter is very smart. Yes, you're perfectly right, but there is something more in biology, because it concerns our health and life.
Questions? Marta and Carlo?
Maybe I can you first as well.
Just you told us about the negative result in logic and mathematics and how they have been so fruitful. I would like to ask you, do you think that in biology we can have something, some analogous negative result that can be fruitful for the future research?
Yes, but you need a theory. So there is an evolution. There is an evolution. Is more a remark, but it requires thinking. It's a result, not in the technical term of mathematics. In theory of evolution, there is a negative result, I would call it so, due independently to René Dom, Stuart Kaufman, and myself in subsequent steps, but we didn't know each other. René Dom makes the very drastic remark in 92, I think. He says, Darwin's theory is not scientific. It's not scientific because it doesn't allow a mathematical description by fixing a priori a phase space. You know, Kantian approach, fix first space and time as conditional possibilities. Physics has been following this paradigm, enlarge the phase space, so also observables. All the theories of physics. The theoretician has to first construct phase space, then looks at the dynamics. Quantum physics, Hilbert space, first, then you see observables will be bounded operators, and so on and so forth. All the physics like that. And as for Tom, mathematics exists before humans, and in mass frame or formal knowledge, he understands the negative result that there is no way to give a phase space an amount a priori of evolution because observable change along evolution. And that's the negative result. For him, it's Darwin that is wrong. For me, is that this way of theoretizing, so beautiful and strong in physics and fundamental for the connection between mathematics and physics, doesn't work. That's what Stuart Kaplan and I independently, 10 years or 15 years respectively, Tom wrote in books, and then we collaborated in developing this idea. The key point is that if you choose the observable according to suitable theory, which is the Darwin's theory of organisms, phenotypes, and populations, then phenotypes change, the observables change with the dynamics. The dynamics co-constitute the ecosystems and the very observables. And this makes the mathematical method as such, as we're constructing suitable, but we have to invent suitable mathematics, as physics has always been done. Physicists invented mathematics, even in the 20th century. Dirac delta, Feynman, integral, Gauss theory, non-commutative geometry. In 100 years of mathematics of priori, this is not a new mathematical concept. This is a proof that it doesn't work. We have to invent new mathematics. Mathematics is not already there, we have to do it. I will not do it. As I said to my best student, my best recent student, your best student will do it. You know, from Galileo to put mathematics in Newton took 100 years. Quantum physics, 30 years to get mathematics after the early theoretical idea. We work at the theory. Mathematics will follow, if it can follow. But surely borrow mathematics from physics is a methodological mistake. That is never done in physics, or very rare it takes. Most of the time, physics has been invented. It's all mathematics. And that's a negative result, if you want.
Mark, you have a question?
Maybe a comment?
Yeah, the last question, yeah, okay.
Okay, if we have time, if not, I think this is more or less a follow-up on Giulia's comment and your first answer. What I'm wondering is whether we can consider this story you have been presenting, distinguishing the debate, for example, between SMT and Toft, as they already do in the literature, in causal and explanatory terms. What I'm referring to is that the debate is on what is a cause of cancer and what is an explanatory account of carcinogenesis, which is not exactly the same, right? Not from a scientific point of view or from an epistemological point of view. So what I'm finding interesting, and I have been discussing in different papers these issues, is that at some point there is a convergence between among different perspectives, making sense of a wider epistemological framework, which is Toft, so epigenetics, environmental factors, and so on. But when we have, for example, a mechanistic account of carcinogenesis, if we analyze the relata, that structure, the explanatory account of that phenomenon, of that process, we can actually find all the dimensions you have been spelling out in your talk. What I'm saying is that when the science works, in the explanatory story they offer, if they work at the right level of analysis, and this is another issue you have been highlighting too, we can find in the way they conceptualize the relato of the explanatory story all the dimension that sometimes seems to be in contrast or even contradictory in different theories or models of these biological processes.
Even within Toft, you say?
I think that Toft has the right framework from an epistemological point of view, and that it can make sense of a mechanistic account, also of a mechanistic account when they work. So for me, this is a way out from a debate among the theories, or right. So, and another way of framing the question you raised at the very beginning of your presentation about the incompleteness or usefulness of models and theories, which is another debate from a theoretical point of view and in philosophy of science, right? Anyway, maybe a comment more than a question, but...
No, but I see that's entirely true. First, on one, I feel very safe, because negative results in completeness are been a locus of exploration from my side, also technical, in mathematical logic quite a lot. So, on one side, it is clear to me that you may have a theoretical frame that is enriched by setting the borders, right? Negative results that on one side reinforce the domain itself is that in mathematical logic, you know more, we have proof theory, finite compatibility. On the other side says what you have to do elsewhere opens new ways, and this happened several times, and that's fundamental. This is very different from analysis of how useful in understanding. The two things are separated. And that's very difficult to explain to my colleague in molecular biology. If you say incomplete, they understand useless. No, and molecular analysis are very important. Right? But as for the causal relation of this conceptual frame, now I know that in physics we can talk without causes and in symmetries. For example, on the grounds of Noether's theorem, unification of gravitation and inertia, in relativity theory, one can say, what's the cause of a falling body? By symmetry. That's beautiful. That's beautiful. We can avoid the causal terminology, and that's a fantastic achievement. It's this great unity about symmetries in physics, which is in biology there is a role of time which is very peculiar, and it's the setting up of the organization. So the causal connection cannot be avoided. If I go to the doctor, I want to say the causes of the pneumonia, and he will say that bacterium. Of course, it is enabled by your lung that are in a situation of weakness, your immune system that did not react to the bacterium, so there is all this contest. But it is fair to say that the bacterium is a cause, and so you kill it with antibiotics. I don't think you can avoid this causal terminology. This is part of the similar in cancer. If I say, yeah, okay, between 5 and 10% of causes is a mutation induced by carcinogen, I'm saying 70, which makes sense. And the other causes, well, is the disruption of cell proliferation or the structures I mentioned before. And which, of course, causes, because of the principle of reproduction with variation, the Darwinian principle applied to organisms, causes variation, a cell that varies, very often varies DNA. So mutations, lots of all kinds. I'm really not so clear. You are thinking more than me, I know, about this interaction between the historical frame. But I would not give up the request in biology for the causal analysis, not for now.
I completely agree on that. The form it takes in biology is functional, so this would be another issue. But,
okay.
So thank you very much. Yeah.
Thank you, Giuseppe. So the session will start at 3 o'clock in the afternoon. Now we have a lunch together.
Where do we go to now?
We're going to go together near the hotel,
Okay.
very close to the hotel.
It's your bureaucratic duties called.
Okay.
Oh, so your signing is necessary for us to eat lunch.
Devo fare anche una cosa di Cesare che ha fatto fuori, ci sono vari visibile. La cosa perché io lavoro grafico, però posso gestire i miei
Vanno bene, però diventano più critici.